So this chapter is about chemistry, and it's not going to be the chemistry that I believe you probably had in high school or even in college. It's a very broad overview of just basic chemistry, and I've tried to turn it into something that's going to be more applied for what you're going to be doing in medic. So here we go. So there's a few definitions that we need to start with. Matter is something that's a big deal in chemistry. It's anything that occupies space and has mass. So it's virtually everything in this world, things that you can and cannot see. Even air has mass. So it can either exist as a solid, which obviously you can see it as a shape, and it's going to have volume, liquids, and then as a gas. And so with a gas, obviously that's very difficult to see. And the two gases that are very important to us in paramedicine are going to be your oxygen and carbon dioxide. And when we get to the respiratory chapter, we'll talk a lot more about how that works. But today, you're going to get an introduction of what that does in terms of looking at the equation that has to do with how our body processes oxygen and then creates the waste product carbon dioxide. So matter can be changed. So physically, that means that you can have changes in the actual state. So you can have a solid become a liquid, and then a liquid can become a gas. And so this happens when you add heat, or you can take a gas and compress it. It can become a liquid then, and then you can actually continue to cool that gas, and it can actually become a solid. So you can change the state of the matter itself, but in terms of the mass and what it has, you can't really do a whole lot with that. So chemically, what we do is we can alter what's called the chemical composition of a substance. And you do that by combining it with other substances, so you can create new things, or we either add heat or remove heat. So we can actually increase energy or decrease energy based on what the state of that particular piece of matter is going to be. So when you look at energy, energy is the ability to do work. And so energy itself is this concept that doesn't have mass, it doesn't have space, but it has what we call potential in terms of it being inactive or stored. So if you think the example this has been used a lot is you can hold a bowling ball, right? You hold it out in front of you. And as long as it hasn't been released or you haven't dropped it, it's going to have what's called potential energy. So it's storing that energy that it has. As soon as you let go, that is now converted into kinetic energy, and that is the actual energy that is doing work. So what our body has is that we have this stuff that's called ATP, and that is the energy that our cells will use to be able to carry on the different metabolic functions. And so our body has to make this ATP. And so when we get to talking about how the cells function, we'll be talking about how it is that our body has this ATP energy, and how when we break the different bonds of the chemicals that are within the ATP, that is what we end up using, because that energy is now released as heat and the cell can carry on and do its different metabolic functions. So our chemical energy is stored in these things called bonds. And here's the ATP that I talked about. The long term for this is adenosine triphosphate. And so what that means is that it has this base called adenosine, and then there are these three pieces of a phosphate attached to it. So you've got adenosine and then a phosphate, and a phosphate, and they're held together. So you have three phosphates. What our body will do is it'll use this to carry on the different metabolic functions, whether it is opening up a gate for within a cell membrane to allow things to come in, or when it's having to reconstitute different pieces of a particular molecule, or when our body is going to end up breaking things down. So we have to have ATP. Our body also uses what's called electrical energy, and the electrical energy is based on the particles that happen to be these things called ions that we have in our fluids inside the cell, and then in our blood, and then also in fluid that is just outside the cell in what is called interstitial fluid. Mechanical energy, this is actually directed in terms of moving things, so we have to use mechanical energy for that. And then radiant energy, this travels in waves, and the things that we use more from radiant energy, these are going to be more things that related to the sun, or when you think of radiation itself, we can use radiation for energy as well. But primarily what we're going to be talking about with the human body is going to be chemical energy that we use from the ATP, and then the electrical energy that results from the movement of the different charged particles that we have inside the cell and then outside the cell. So we have these things called elements, and elements are these units of matter, and they have these things that are called protons and neutrons and electrons, and they're all contained in this little element piece that is made up of atoms, right? And so an atom is this thing that is going to make up this thing called an element. So we have things called oxygen and carbon and hydrogen and nitrogen. And I think you've heard of these before. These are very, very important elements that are part of the human body. So this is the periodic table of elements, and what you see is a whole bunch of letters, similar single letters, and the others are going to have two little letters with them. And what you have up here, this is called hydrogen, and hydrogen has an atomic number of number 1, and you'll see that it's listed over here. And I'm not going to get into how the whole table of elements is organized, but a lot of it has to do with the actual reactivity of the element itself, and then what happens when it combines with other things. And you'll see some of these equations and different things in a few slides. But what I want to point out here is that every element is going to have an atomic number. So, for example, with hydrogen, atomic number is 1, because this one only has what's called 1 proton. It doesn't have any neutrons, and it also has 1 electron, and we'll get to that in a second. You'll also see that it has the atomic weight, and this is basically the mass, or how much, we think of things as in terms of pounds and ounces, but atomic weight has to do with the number of protons and the number of neutrons that an actual element has. And so we'll get into that in a little bit. What I also want to point out is that you'll see that some of these elements have 2 letters in terms of their names. So like this is magnesium, Mg, and then over here we have manganese. They both start with M. So this is why these two have 2 letters based on their name. But then you'll also notice that they have a different atomic number. Manganese is 25, magnesium has 12. Magnesium happens to be a metal that we have in our body. We'll get to that in a sec. You also give magnesium as a drug, medication that we treat sometimes for asthma, sometimes for cardiac issues, and then sometimes for pregnancy issues for people that are having seizures. So there's a number of elements that you see here that have now also been used in the components of medications that are important in the body. And then these elements also are part of what conduct electricity in our body. So for example, sodium and potassium, very, very important in establishing cell membrane, what we call polarity, which means that there's a difference in the charge from the outside of a cell to the inside of a cell. We'll be getting to that in the actual chapter that has to do with the cells and the tissues. Then the tables that you'll find in the textbook, they'll go through and they will list, the name of the element, they'll give you the atomic symbol, and then the percentage of the body mass of what is found within our body. It also tells you what the job is of that particular element. For our purposes, you don't need to memorize these tables. We'll be talking enough about these in the concept of what it refers to in terms of being a paramedic, and then how it applies to the human body as we get to their role in the subsequent slides and subsequent chapters. So here's some other ones. Calcium, for example, very, very important for a muscle contraction. Phosphorus is very, very important, again, with ATP, and also the role that it plays in this thing called phosphate. That is also extremely important in terms of balancing the internal balance of the cell in terms of electrical conductivity. Same with potassium. Sulfur is really critical in terms of bonding and how we make proteins. So we'll get to all that. All right, so this is what an atom looks like. So we have 2 models. So for example, this one here is called a planetary model, and we'll get to the other one. It's more of an orbital type model. But what you see here is the element itself. So the chemists, what they do is they draw these things out. And what you're seeing on the outside here, all right, here's your helium, for example. Helium has 2 protons. That's what this little guy here is, so 2p. And inside the little circle thing, okay, there's this thing called a nucleus. So in the nucleus of the atom is where you have your protons and your neutrons. These electrons, these little guys out here, these are the ones that are going to combine with other atoms, for example, to then make different compounds or different molecules when you combine 2 of them, for example. So, but that is how we actually show, okay, well, what does an atom look like? And this is the most common model that you will see in terms of what it is. A proton, again, in this case, they've symbolized them in red. This is what would be called the nucleus of the atom. And protons themselves have a positive charge. So I always remember proton starts with P, so they're positive because positive also starts with P. A neutron is neutral, so neutrons do not have a charge, so that's why they start with N for neutral. And then electrons are negatively charged particles, and that's these little guys that are actually spinning around the nucleus itself. So what you're seeing here, this is what a helium atom would look like. So it's going to have 2 protons, and you'll see that it also has 2 electrons. When the protons and the electrons match in terms of their number, that atom is considered to be neutral. When you have the different number of protons, different number of neutrons, that's going to actually change a little bit in terms of how an atom is going to behave. So we'll get to all that in a little bit. But what I want you to remember, and things that I'm going to ask you on the quiz and also subsequently on the test, is that protons are positively charged, neutrons are neutral, and electrons have a negative charge. So when you look at neutrality, remember that if the protons equal the number of electrons, so what you see here, that means that it's neutral, all right? The positive and negative charges cancel each other out. Now, atoms can lose an electron or gain an electron, and when that happens, they are what we call ions. A cation, and you'll notice this T here looks like a positive sign. What happens here is when an atom has actually lost an electron, so it got rid of negativity. When you lose negativity, you become more positive, just like in real life. When you get rid of a negative thing in your life, you actually hopefully become more positive. So the word for a positively charged ion is called a cation. An anion is an atom that gains an electron, so it actually gains negativity. And so now it has an additional negative electron on it, so it causes it to become negatively charged. So what I want you to remember about this is that a cation is a positively charged ion because it gave up an electron, and then anion is a negatively charged ion because it gained an electron. So this is an example of what it would look like. So what you see here, these are the electrons spinning around the shell. And sodium itself, when you look at its outer shell, it only has one of these little electrons. Over here, chlorine has 7. 1, 2, 3, 4, 5, 6, 7. The happy place for this outer shell of all these different atoms that we're going to be talking about is when you combine things, they want to be whole. And whole means they want to have 8 as a minimum on that outside shell of the electron when you're combining some of these things. So 8 is kind of its happy place. So you notice that this guy, it is much easier to give up the 1 electron to chlorine, right? And then chlorine accepts that, and now it has 8 electrons on the outside. So when they combine, now what we have is a positively charged ion, sodium, because it gave up that 1 electron on the outside, so it got rid of negativity by giving it over here to chlorine. And then chlorine gained that electron because now it has 8 on the outside. Normally it would just have 7 when it's neutral. And so now what happens is, now it has 8. And so what we formed here is what we call an ionic bond. So when you have 2 elements that come together where one gave up an electron and the other accepted it, now we have a positively charged ion, a cation, and now we have a negatively charged ion, an anion. These two, when they come together, they can attract because you have positive and negative. Those 2 charges attract, they don't repel each other, and they form what is called an ionic bond. So that is how it is that we come to have ions that are positively charged, a cation, and then an anion that becomes negatively charged. So when you're looking again at this planetary model, and we have the orbital just means you've got this like wave of energy floating around. The planetary model kind of looks like the planets, right, orbiting around the sun. This is the one that for me makes a lot more sense because you can actually visualize what is taking place with those electrons that are spinning around the actual nucleus. So when we look at what we talked about, the atomic number, remember that the number of protons are going to be what gives an element its atomic number. So in this case, helium has 2 protons, which means its atomic number is now going to be 2. The atomic mass comes down to protons plus the neutrons. Protons have weight, a mass. Neutrons have weight, a mass. So when you add them together, that is what makes up the atomic mass of the actual element. The atomic weight, this one's a little bit goofier because now what happens is in some cases you can have elements that lose neutrons or gain neutrons. And in those cases, that's going to change the actual weight of the element itself. So that is what they call an isotope. So when you look at the actual weight of an element, you're looking at what is the most abundant isotope, the one that you would find most commonly. All right, and that's what they refer to as atomic weight. What I want you to remember is that the atomic number is equal to the number of protons, and that atomic mass is protons plus neutrons. Here's an example of what an isotope would be. So here's hydrogen. Hydrogen has the atomic number 1, and it actually does not contain any neutrons. However, if it gains a neutron, now we've actually changed it, and now it becomes this thing called deuterium. If it gains 2 neutrons, now it becomes this thing called tritium. So it changes. But these two over here, we still have 1 proton, which says this is still hydrogen, but it has an isotope because it's now actually gained a neutron. And then over here, tritium actually gained 2 neutrons. So it's also an isotope of hydrogen. So an isotope has the same atomic number because it still has the same number of protons, but the atomic mass is going to differ because the number of neutrons is what changes. So for an isotope, if I ask you a question about this, I want you to remember that an isotope has the same atomic number, same number of protons and electrons, but it's going to differ in the number of neutrons. When you look at just the list of different elements that we have, so here's calcium, for example. So calcium, very important in terms of muscle contraction and signaling for our neurons or brain cells to function. Its atomic number is going to be 20, so it has its number of protons as 20. Its atomic mass, the protons plus the neutrons, is 40. And the atomic weight itself, remember this has to do with the abundancy of all these different isotopes that we would have for calcium, and that is, as a whole, what the atomic average weight of all the isotopes would be. So that is kind of what that comes down to. Now, when you look at a radioisotope, what this is we're looking at isotopes of certain atoms. For example, plutonium, very, very common isotope that is considered to be radioactive. Uranium is another one. And what happens with these is that they tend to be unstable. So what that means is that these isotopes are continuously decomposing because they want to reach stability. Isotopes don't like to be unstable. So in doing this attempt to reach stability is what causes these things to become radioactive. So what they start to do is they lose these little particles, and then we can actually use these particle losses to trace different biological molecules. So for example, sometimes you can go and get an MRI done and they will use a radioisotope, not something that is radiating you. You're not getting all this exposure to massive amounts of radiation, but it's very, very light, and it's able to actually help the radiologists see different things in our bodies on CT scans or in some cases in MRIs, so that they can actually find and determine if there are parts of our body that are actually, for example, if they have a cancer. Right? They can actually identify these. They can also find, using PET scans, different cells or areas in the body that are not working properly. So we use these radioisotopes for that. As you know, radiation is also a weapon. So it can be used in nuclear devices, and what happens there, and obviously when those blow up, they create a very, very large explosion, and a lot of power comes out from that. So it basically disintegrates everything in its path. But what also happens is that the decay, the radiation that is left from the waste, it will continue to decompose, and part of that is then what ends up making many, many individuals sick because of that decaying and decomposition of that particular unstable isotope. So that's pretty much all I'm going to talk about with radiation and radioactivity. But radioisotopes, I just want you to remember that why they're radioactive is because they're in this continuous state of decomposition. Some of them are a lot more stronger than others, and some of them are not going to be as toxic or decay as rapidly. Then molecules and compounds, this is when we are putting together atoms, and again, how they're going to combine and how they function has to do with the way that they react based on what are the electrons doing on those outer shells. So when we put two atoms that are the same together, that is called a molecule. So for example, here's an example when we take hydrogen plus hydrogen, and that would make H2, because now you have two, and this is called hydrogen gas. So if you think of it in terms of food, and I love using food as examples, you take one tortilla plus another tortilla, now you have two tortillas, so it would be a tortilla molecule. The other thing that I want you to understand here is that on the left, these are considered to be the reactants, so the things that are going to cause a reaction when they combine. And then what you get on the right side is now going to be what's called the product, based on the combination of the reactants. In this case, we have a molecule. We just had two things come together, and now we have our hydrogen gas, or we have our tortilla molecule. In other cases, you can have other things that are not the same combined. So here, for example, we have 4 hydrogen atoms that combined with 1 carbon, and now we make this molecule or this compound that's called CH4, which is methane, right? You've probably smelled methane. It smells like rotten eggs, and it's a gas. If you think of it in terms of just a boring taco with carnitas, if you have 2 tortillas plus, say, a cup of carnitas, now we have 1 cup of carnitas plus 2 tortillas. We can make 2 carnitas tacos, right? Because now we have our 2 tortillas plus the 1 cup of carnitas. So we're actually able to split that up, and we have 2 tacos. So here's our reactants. So the things, the ingredients that are going to make up the product on the right, and we have our product based on the reactivity of the reactants that were on the left. In this case, you can see we've got 2 chemicals that are very common in nature. We have sodium. Sodium is actually a metal. Sodium by itself is very, very reactive. If you add water to sodium, it can cause a very, very strong reaction. Not a good thing to do. Chlorine by itself can give off a very poisonous gas. But when you combine sodium plus chlorine, you actually make a compound called sodium chloride, which is very safe, very neutral, and we know it as table salt. But each individual reactant, each element by itself, is very, very reactive. Put them together, they neutralize each other, and now we have a nice, happy compound that is not going to actually cause problems. So when you look at how is it that these atoms react with each other, what they end up doing is that they form these things called bonds. And the bonds have to do with how did these atoms work together in terms of what did the electrons do when they combined. So for example, here we have 2 hydrogen atoms. So we add 1 hydrogen plus another hydrogen. Here's the electron, here's the electron. Now remember, this is now an odd number. We don't like odd numbers. One easy thing to remember is that the very first shell that is around that nucleus, its happy place is the number 2. So if it can find another atom where it can either bond to another atom and form a pair, like we did here, this is now a shared bond. This happens to be called a covalent bond. But what we have now is a shared pairing of the electrons. And so this is our hydrogen gas. Over here, here's oxygen. If you look at oxygen, we have 1, 2, 3, 4, 5, 6 electrons spinning around on the outside. When we combine these two, what will happen, because we want to have a happy number of 8, because now we're in the second shell here. The very first shell likes to have 2, and then the next shells thereafter, their happy place is to be at a minimum number of 8. And so what will happen is, because we have 6, we want to get 2 more. So that's very easy to do when you combine these two, oxygen plus oxygen, we put them together, and now look, we can actually share 2 electrons from each, and we end up having a nice little pairing, or what we call a double bond. Here have these two little lines. So what the chemists do when you have equal sharing of electrons, what we call a covalent bond, and I'll show you this in a little bit, they actually draw two lines, and that's what we call a double bond. Up here with hydrogen, we had a single bond, but it's equally shared because it just goes straight across. Down here with our methane, we have our 4 hydrogens. Remember, they each had just 1 electron spinning around. Carbon has 4 electrons on its outer shell. It wants to have 8, so it's able to now pair up with hydrogen, 1 electron on each, and now we have a very happy stable molecule of methane because now we have shared electron pairs in those outer shells. So now the hydrogen is happy and the carbon is happy. So we're looking at when these chemical bonds form based on what is the behavior of these electrons on the outer shell. So electrons, as you can see, are very important things when we're looking at the elements and then how they're going to react together. And I talked about these things that are surrounding the nucleus, the little circles. Those are called the shells or the orbitals. So the very first orbital likes to have the number 2. All right, that's its happy place. It needs to have at least 2 electrons spinning around. The next shells and the subsequent shells, their happy place is to have a minimum of 8 in order for it to, find its, basically think of it as its true love. So it can find its true love by either giving up an electron if it's going to end up being an ion, or it can equally share with another atom and share the space. So happily thereafter, think of it as a very, very happy marriage where they have equal sharing of the actual electrons. So the actual bonding, like I have written down here, involves the interaction between the electrons in the outermost shell. So when we look at this, again, the very first shell likes to have a maximum of 2. The second shell, its happy place, likes to have a maximum of 8. And then third shells can have a maximum of 18. So they just keep increasing in terms of the number of electrons that they can hold. For our purposes and what we're going to be looking at and going through today, it's just going to be some very simple bondings, just so you can get the idea of what a covalent bond is, what a polar bond is, and what an ionic bond is. And then we'll talk a little bit also about hydrogen bonds and why those kind of matter in terms of keeping things together. So this thing about the rule of 8s, right, I kind of talked about that already. When you think of an atom, what we call inert, right, that is an atom that is going to be stable when its outermost shell has 8 electrons. So when you look at neon, okay, here's neon, its atomic number is 10. It has 10 protons, and then it has 10 electrons total on the outside. So when you look at it, you've got first 2 electrons in that first shell, which is what it wants. And then look at that, it has perfect 8 electrons on the second shell, which is what it wants to have. Because the number of protons is 10 and the number of electrons is 10, this is not going to be taking up a whole bunch of others, right? This guy is not going to be hooking up, doing other things because it's got its happy place. As you can see, it's got its 8 electrons here. So this is considered to be inert. When we have our reactive elements, remember this now has to do with what the electrons on the outer shell are going to be doing, whether it only has 1 shell, which is the example in hydrogen where it has only 1 electron, or you look at carbon, right? It had 6 in its outer shell. It happens to be the second shell. This guy wants to have 8 on that outer shell. So it will actually go, it has 4. So it'll pick up 4 more electrons. Easy place to get that, boom, is from hydrogen. Oxygen itself, this one has 6 electrons. It wants to pick up 2 more so that its outer second shell can have 8 electrons. So that's how they go through and they start doing their different bondings. So when we look at what's called a covalent bond, right? Covalent bonds, remember, are going to be sharing an electron pair. So for example, here with hydrogen, we have 1 electron plus another electron. They come together and now they share the bond. So this right here, they're equally sharing the electrons. So now we have this first shell. It's stable now because it's sharing that with that second electron that came from the other hydrogen, and now technically these two are in their happy place. So it's equally shared. No one is tugging for more in the relationship. When you look at what happens with two oxygens coming together, here we have 6 electrons on the outside. Remember that they want to have 8 on the second shell. So when we put them together, now we are able to equally share with these pairs here. So the 2 here from this particular atom, and then the 2 over here from this atom. Now we have this equal sharing, but because we now have 2 pairs of electrons that are being shared, now we're making a double bond. So that's what the 2 little lines mean. We can also have up to other molecules. So here we have our carbon. Here's our oxygen. You know, this is carbon dioxide. The word di means 2. And so what this is telling you is that you have 1 carbon and 2 oxygens. So what is happening here is we have oxygen sharing with the carbon and then another oxygen. Oxygen, remember, this one has 6 electrons on its outer shell. Carbon has 4, and then this one here has 6. So what ends up happening is we pair up, and now 2 of these carbons will share with 2 of the oxygens on the outside to make a complete orbital. We now have 8 happy places, and then same thing on this side. So now we have carbon dioxide. So what is happening here is we have equal sharing between the molecules, and this is what's called nonpolar. When you hear the word polar, what I want you to remember is that now there's some tugging, all right, some giving up and taking within the relationship itself. So what that looks like is this. So here you have oxygen, and then we have hydrogen. Remember that hydrogen has 1 electron. Oxygen itself on the outer shell had 6. And so what ends up happening with this, in order for us to have this, I'm now complete with oxygen, oxygen is very, very attractive because of those 6 electrons that it has on the outside. And hydrogen doesn't like to be by itself. It wants to go and join oxygen. And so what happens is that that electron that hydrogen has on its orbital is actually attracted to that outer shell of the oxygen much more strongly. So what happens is that this hydrogen will actually give more, right? The oxygen will actually pull and attract that hydrogen more forcefully than what you see back here when you have carbon and then oxygen coming in. You don't have as strong of an attraction. So here you have equal sharing. But with hydrogen, now we have polarity, which means they have some positivity within the bonds that are being formed, because this electron that hydrogen has on the outside is actually being pulled more strongly by oxygen, and oxygen is kind of hanging on a little bit more tightly. So this is why we call it polar. So the electrons themselves are not shared equally, because we have a little bit of this give and take, giving up. So hydrogen is kind of giving more of itself to the oxygen, and that's why it becomes more positive. Remember, when you are giving away negativity, that you're going to gain positivity, and then the oxygen itself is actually now gaining some negativity from that electron from hydrogen, and that's why this one ends up becoming more negative. So that's what a polar covalent bond means. So when you look at nonpolar covalent, that means there's perfect equal sharing. Think of it as kindergarten with your best friend. You would skip down the hallway holding hands, no conflict whatsoever, everybody's happy. And now we get to junior high, you're still friends, but hey, you know what? Now one of you is actually going to have a little bit more pull, maybe exert some peer pressure, and have that electron kind of pull more toward that oxygen molecule. So now we have polarity. So the molecule itself actually has a more positive and a more negative side. This happens to be what water looks like. When you put a bunch of individual water molecules together, what ends up happening is that each individual molecule, because now we have hydrogen, oxygen, hydrogen again, the hydrogen on one of the molecules will have this very slight attraction to an oxygen on another one of the water molecules. And so what you see here, this is called a hydrogen bond. Hydrogen bonds form from the hydrogen atom on a particular molecule to another atom that has some of this pull, or that hydrogen being somewhat attracted to that other compound or other molecule that is coming by. And so what chemists do is that they depict this by having just little dots, and that is what we call these hydrogen bonds. Hydrogen bonds are actually the weakest type of bonds that we have in nature and in the human body. Right? These can be very easily broken up by heating. So as you know, when you boil water, it becomes steam. So what ends up happening is by creating that energy, you're actually causing these here to break apart, and they become water vapor. So you separate, you make them further apart. When you actually cool or freeze water, what you're doing is you're causing the separation here in these hydrogen bonds to actually get much closer together, and it tightens up that the molecular structure of all these individual water molecules, and it pulls them closer together, and then that is what then ends up forming ice. When you add heat, they start to separate, they become a liquid. You continue to add heat, then it can end up becoming a vapor. When we look at ionic bonds, now remember, this is when an atom is fully giving up an electron to another to form the bond. So I showed you this earlier where we had the example of sodium, which only has one electron on its outer shell, which makes it very, very reactive. It wants to give that up. And then you have chlorine, which will become a chloride atom when this sodium gives up its electron. And so sodium gives it up, chlorine accepts it, and now because chlorine accepted this negativity, now it becomes what we call the chloride ion. And you'll notice that we have this little symbol right here, sodium now has positive, that tells you that it gave up one electron. Chloride ion tells you it has one little negative symbol right here. It tells you that it now gained one electron. Say, for example, we had given up 2 electrons. So in the example of calcium, when calcium forms an ionic bond, or when calcium becomes a cation, it actually ends up giving up 2 electrons. So with calcium, you would have a little 2 here and the positivity. So remember that with ionic bonds, these form when electrons are completely transferred from one atom to the other to make that bond. And so the ions will result from the loss or the gain of an electron. Anions, remember, have a negative charge because they gain an electron, and cations have a positive charge because they lose an electron. They lose negativity. So that's where these little pluses and minuses come from. Now, in terms of the chemical type of reactions that we can have, so remember earlier I talked about the reactants being the things on the left, and then on the right you're going to have the product. So we have these things that are reactions where you're going to make stuff. When you make something, it's called a synthesis reaction. So in this case, for example, A plus B made a product called AB. So if you think of it as a tortilla plus some cheese makes a product called a quesadilla, right? We combine the tortilla with the cheese, and now we have this compound that is called a quesadilla. So what happens is you have atoms, or you can have molecules. So you could have multiple reactants that have more than just one actual element, and then they end up forming more things. And I'll show you an example of that in a second. But what ends up happening when you do a synthesis reaction is that energy is actually absorbed for that bond formation. So when energy is absorbed, which means you're not losing energy, nothing is being decayed or given up, it's called anabolic. Anabolic means to build. So when our body is making protein, for example, you go work out, or you're lifting, you're stressing that skeletal muscle, the skeletal muscle is going to say, hey, if you're going to keep doing this to me, I need to get stronger. I need to get thicker. So what that does is that it triggers that skeletal muscle cell to synthesize more of the proteins that are going to strengthen the muscle and make it thicker. So what it does is that it uses these individual units called amino acids. So we depict them here as these little orange dots. And then when you put them together, so you see these little lines, okay, each of these little lines is a peptide bond. A peptide bond is a bond between 2 amino acids. And so what we did here is we built, right, so we anabolized, we used the process of anabolism, which means to build, to make this new molecule. We put stuff together. So I want you to remember that anabolic means that you're building things, and synthesis reactions are going to be doing this. When you have the opposite, so now we have something that is going to break apart, now we have our product decomposing, so you're breaking it up back into the reactants. So here we had AB go back to A plus B, or think of it as here you have your taco, so you had your tortilla with your carne. Now we're going to break it up, we're going to separate them on the plate because now you decided, hey, I don't want them together. And so now we split it up and you can have your individual tortilla and then your carne next to it on the other side. So now you've made it into a smaller particular molecule. So when this happens, when you have a decomposition reaction where bonds are actually being broken, these are called catabolic. Energy is being released when this happens. So all the catabolic activities that are taking place in our body are actually, don't think of them as destructive in a bad way. You're just breaking things apart because in some cases you need to use the energy from the bond that gets broken up, and then maybe you're going to be using some of these particular individual elements to now make some new things. So you can actually decompose stuff and then make new stuff from the ingredients that you broke apart and then build new stuff. So if you think of it kind of like Legos, right? We've got our little house that we built and now, hey, now I want to make a car, or I want to make something that looks like a rabbit, whatever. You take your individual little Lego bricks and then you can rebuild them into something else. But before you do that, you have to break apart the actual original structure. So that's an easy way of thinking also of these decomposition reactions. Here's an example of a molecule called glycogen. Glycogen is a sugar that is stored in our liver and in our muscle. We use that for energy, very, very important molecule. But when it's broken apart, to break it down into its individual glucose molecules, which is what our cells need for energy, we have to break these bonds up. And so when we break up these bonds, now we're taking this nice glycogen molecule, causing energy to be released from each one of these little breaks that we bust up, and now we have individual glucose molecules, and then the glucose can be used. When you have what's called an exchange reaction, which is a lot of what we do in our body, you have different elements that can be exchanged. So here you have the product of AB, and in this case we can do an exchange where now we combine it with this other element C, and we can have AC plus B. Just an easy way of doing that. In this case over here, we could have two different compounds. So now we have AB plus CD, and then we can recombine them to make AD plus CB. So you can do these type of exchange reactions where you have simultaneously a synthesis and a decomposition reaction taking place. So hopefully you can understand that these are going to be a bit more complicated, and if you think about it, these types of reactions are actually going to require more energy in terms of what we're going to be doing. So we're going to be creating energy when we break up these bonds, and then we actually build things back up and then absorb energy again when we get our new products. So our body is continuously doing this. When you look at this in real life, so earlier I gave you the example of carbon dioxide, right? We've got carbon, and we're going to combine it with two molecules or two atoms of oxygen that are put together. So we've got here oxygen gas. So when you get carbon plus oxygen gas, O2, we end up making carbon dioxide. Nice, easy synthesis reaction. If we want to decompose, so earlier I talked about glucose, for example. Glucose, its actual molecular formula, has 6 carbons, 12 hydrogens, and 6 oxygens. So this particular molecule, we looked at it as a whole, and I don't have a picture of it here, but I'll show you an example a little bit later. Okay, we take glucose, we react it with oxygen gas, and what ends up happening is we get the byproduct of carbon dioxide and water. So when our cells are using glucose for energy, oxygen is very, very important because of the aerobic metabolic process that we're going to use because we're utilizing oxygen. And we're able to make the energy that the cell needs. It's called ATP. But the byproduct, the waste product of this, is going to be carbon dioxide and water. This carbon dioxide that builds up, our body can't use that. It actually becomes a waste. And one of the things that we don't want with carbon dioxide building up is because carbon dioxide will continue to react with the hydrogen ion, or with the water molecule. And what will happen is that we will now have this thing called carbonic acid. So to make it a little more complicated, here's what happens. At the tissue level, think of it as your skeletal muscle. We use glucose for energy, brought oxygen into the mix because we needed to make a lot of ATP. In that process, we made these byproducts, carbon dioxide and water. And then these two, when they combine, they actually make an acid. This right here is called carbonic acid, H2CO3. This carbonic acid, what it does is that it'll actually dissociate. It'll break apart, right? It'll decompose. But it decomposes into hydrogen ion and this new ion called bicarbonate. And you'll notice that the hydrogen ion has a plus charge and the bicarbonate ion has a negative charge. And so what happened here is that the electron from this hydrogen actually ended up being taken up over here by this oxygen. And so that is how this anion, bicarbonate, came to be, because this guy here actually accepted the electron from one of these hydrogens. We'll get more into that when we get to the respiratory system, but I wanted to give you a relevant example of part of what happens with the tissue metabolism at the cellular level. So, our tissues used the glucose, they made carbon dioxide and water, that got converted to carbonic acid, and it dissociated, means it split apart into this hydrogen ion and bicarb. Now why this matters is that this stuff is in our blood, all right? So we've got bicarb, now we've got hydrogen ion. One of the things that happens with hydrogen ion is that it causes things to become acidic. Bicarbonate ion is what we call a base, and we'll get to why that matters in a little bit. But what our body needs to do, remember, we made this waste called carbon dioxide. So we need to get rid of this. So what happens is in the blood, this carbon dioxide, when it combined with water and became carbonic acid and then broke up, this CO2 here is actually now embedded inside this bicarbonate, right? And so what happens here is when we get to the lungs, so our blood will flow back to our heart, get pumped to our lungs. Now we can actually take this carbon dioxide that is within this bicarbonate molecule and combine it again with hydrogen. So we have this reverse reaction that occurs at the lung level within our blood. These two combine. So they reconstitute, they become back to being carbonic acid. And then what's really cool, through the magic of enzymes and different things that happen on our red blood cell, this carbonic acid returns to being water and carbon dioxide, and then we exhale the carbon dioxide and water. And so that is how our body is able to get rid of this waste product, carbon dioxide, that we have. So here's an image of what happens. Here's the tissue cell. So remember that at the tissue level, the body went through, it had glucose that got metabolized, and it made this carbon dioxide and water waste product. It's going to diffuse from the tissue across this space. This is called the interstitial space, where we have a little bit of fluid between the cells of the tissue and the capillaries, the vessels where blood is carried. These gases go across the membrane, and then we have that combination happen within the blood. And so we have carbon dioxide plus water makes carbonic acid, and now we dissociate into hydrogen ion and bicarbonate. What our red blood cell is carrying is going to be oxygen. On the red blood cell, we have a protein that's called hemoglobin that carries the oxygen. So what happens when this red blood cell with oxygen on it, you have oxygen that is going to come off. It's going to go into the cell. And then as this oxygen is going into the cell, the carbon dioxide that was produced from the metabolism of the glucose actually then diffuses out. So we have CO2 leaving and O2 coming into the tissue. Now what happens at the lung level, so this blood here gets transported back to the lungs. And now remember that in our lungs, we took a breath in, so we took in oxygen, and now this oxygen that's in the alveoli, which are the little air sacs in our lungs, is going to diffuse across the membranes, load onto this red blood cell, and attach to the hemoglobin. What happens at the exact same time as this is taking place is now we have bicarbonate and hydrogen ion combining, making carbonic acid, and then dissociating into CO2, carbon dioxide, and water. So now what happens is the CO2 diffuses across into the alveoli, and now we will exhale out this carbon dioxide that our body is trying to get rid of. So at the same time as the oxygen loads, we have carbon dioxide unloading into that alveoli so that we can exhale it out. So this is a really easy example in terms of how we're doing these simultaneous synthesis and decomposition reactions and then creating these exchange reactions, which again is the combination of synthesis and decomposition at the same time. When we get to the respiratory system, we're going to spend a lot more time talking about how it is that this works. Then in terms of things that cause chemical reactions to happen, right? So we can increase the rate or slow the rate. So how this occurs, temperature is one of the easiest things that we can use. So when you add temperature, so you make things warmer, you increase what's called the kinetic energy of molecules. They move more rapidly and they collide more forcefully. So that causes the rate of the reaction to go up. If you increase the concentration of the reacting particles, you can also increase the rate of the reaction. So you have more things crashing together. And the way I always think of this is you've got more people and you have a mosh pit, you have more people bashing into each other and you have a better mosh pit. So by increasing temperature and also increasing concentration of reacting particles, you can actually increase the rate of a chemical reaction. You can also make the particles smaller. Smaller particles are going to have more kinetic energy and they can move faster and cause more collisions. So the way I always think of this is when you think of kindergarten class, right? You have smaller little humans. You tell them you've got ice cream coming, right? And now you're going to have way more crazy ass collisions taking place running to the little ice cream truck. Then we have this thing that is called a catalyst. And a catalyst is something that causes the amount of energy needed to cause a reaction to decrease. So it kind of helps, all right? It's like having a buddy for this reaction to take place. And so what it does is that it actually holds the reactants in place and allows for the reaction to take place more easily. So you don't need as much energy. So if you think of it as you have bad guys, right? And so now you're going to set up an ambush. So it's much easier to have this spot where you're going to do the ambush. You don't need as many troops because we have this ability to be able to lead them into this ambush zone and then blow up the bad guys, right? Just easy way of thinking about this. Then in terms of the type of compounds that we have things that are called organic and inorganic. All you need to remember about this, and really for our purposes as a whole, it's not going to really matter with the body, all right? We're going to have carbon in virtually every single organic type molecule that we have in our body. So if it has carbon, it's considered to be organic. If it does not have carbon, it's considered to be inorganic, all right? When we have a carbon-containing compound, which means it's organic, these are going to be more what we call covalent. So they're going to be forming covalent type bonds. Those molecules that do not have carbon as part of the molecular structure, they are not going to be making these covalent type bonds, whether they're polar or nonpolar. Those are the type of bonds that will be made more when we have ions taking place. So they're more going to be the ones that are going to, inorganics are going to be making more of these ionic type bonds because they do not contain carbon. Water is a very important compound in our body. It's actually inorganic because it does not contain carbon. So water is, remember, is H2O. So it's made up of hydrogen and oxygen. Water is very important because it has the ability to deal with heat very, very well. It is polar, which means we can actually dissolve things in it. And remember, it has a slight negative and a slight positive charge based on the way that hydrogen and oxygen behave together, but it's not a very highly reactive compound. It is not going to be dangerous by itself. What it also does is it helps provide some cushioning. So if you think of your brain, our brains are sitting in cerebral spinal fluid. CSF is made primarily of water, and it's going to contain some ions. But water is very important for that. So water is a really critical compound that we have within our system. So again, high heat capacity. It can absorb and release very large amounts of heat. And it also helps us in terms of being able to regulate these sudden changes in body temperature that can take place based on what our hydration levels are. And obviously, it makes a lot of sense that, of course, we live here in Arizona, and if you're a firefighter, hydration is absolutely critical in order for you to be able to do your job. Now, when we look at the polarity of water, it's what we call the universal solvent. So we can take this in liquid or gas form, and it can dissolve smaller amounts of solutes. So you can dissolve a lot of stuff in water. A solute is the thing that we're going to dissolve into the water. It could be a solid, it could be another thing that is a liquid, or it could be a gas that's suspended within the actual substance. So we can take carbon dioxide, which is a very soluble gas, and put it into water, and now we have gassy water, right? Club soda. A solution is what forms when the solutes are very, very tiny. And then what we have with a colloid, this is when we have solutes that are of more intermediate size, and they tend to form more of a translucentish type mixture. Now, the chemical reactivity with water, right? I've talked a lot about being very, very important. When we have something that's called a hydrolysis reaction, this is when we have molecules or we have compounds that are going to come together, they're going to cause a reaction, and they require water. But what is going to happen here is that we are breaking apart the water piece of the actual molecule. So this is one of the things that happens when we digest food or we're breaking down other biological molecules. The cushioning piece, remember, is the protective function. I gave you the example of the CSF. So this is your cerebral spinal fluid that helps protect your brain. You can also think of amniotic fluid that has a very high concentration of water that is actually protecting the developing fetus within the mom. Then we have salts and what we also refer to as electrolytes. So if you think of sodium, potassium, calcium, and magnesium, so this is the actual abbreviation for sodium, Na, and because it's an ion, remember if it's positively charged, it means it gave up its electron. Sodium is a very important electrolyte, and we call it electrolyte because what happens with the behavior of the electrons leaving and then when other ions accept it, we actually have an electrical charge that is created. When we get to talking about the cells in the cell chapter, we'll talk a little bit more about those types of reactions. Potassium, the symbol is K. This one also gave up an electron. Calcium, Ca, is its symbol, and it gives up 2 electrons when it causes a reaction with another atom. And then magnesium also gives up 2 electrons. So what we have here are positively charged particles. These can conduct the electrical currents. We have others that are going to be the anions. Remember, those are the ones that accept an electron. So an example of that, for example, would be chlorine or phosphate or bicarb. Okay, but either way, we can actually take these electrolytes and put them in water, and we can actually break them apart very easily. So we can take sodium and potassium, which are very, very important for nerve impulses and also for muscle function. This is what will end up causing an electrical charge. So what you have here, you guys know that water conducts electricity very easily, right? You never want to be standing barefoot in water when there's a a line that came down, an electrical line in it. So what we have here is just an easy example of what water does. So here's our water, right? And so if we take sodium chloride, so here's salt, right, just a little block of table salt, and we drop it in the water, what will happen is that the NaCl, which was in this little brick, will react with the water, the H2O. Remember that the water is polar, which means you have a little bit of positivity, a little bit of negativity taking place here. And this water molecule will actually break up, it'll start attracting the individual ion component of sodium chloride. So we take sodium, that is a positively charged ion, it's a cation, and the sodium will become attracted to the oxygen, which, as you know, is more negatively charged. Then the hydrogen itself, hydrogen, remember, has a more positive charge, so what it's going to do, it's going to attract the chloride, which is negative. And so the hydrogen will actually surround that chloride, the oxygen surrounds the sodium, and then that is how we are able to dissolve salt into water. So this would be an example of that ion in solution. Two things that are very important in terms of these inorganic compounds that you need to understand is the concept of acids and bases. Acids are going to make things acidic. Bases are going to make things basic. So first with acids, what I want to make sure that you understand is anytime hydrogen ion, remember this is a cation because it's positively charged, which means it gave up its electron. Hydrogen ions cause water to be acidic. So what you're seeing here is you had hydrochloric acid, hydrogen plus chlorine make hydrochloric acid, which is one of the strongest acids that we have. When it breaks up, you see here how it completely splits up. Hydrogen gets away from the chloride 100%. This is considered to be a very strong acid because now these hydrogen ions are free inside the fluid. When you have a weak acid, so here's an example of the carbonic acid I showed you earlier from the reaction when water combines with carbon dioxide. When you put this back into water, what will happen is it dissociates into the hydrogen ion and the bicarbonate ion. But not every single one of these compound molecules is going to break up. You still have some that stay together. So that is why it's considered to be a weak acid. So a strong acid is going to completely dissociate, which means the hydrogen ion will completely break apart from the other ion that it's bonded to. A weak acid will only partially do that. So only some of the hydrogen ion and the other compound that it's bonded to, the bicarbonate in this case, will break apart, but not 100% of the time. So that's why it's a weak acid. When you look at a base has what we call hydroxyl ions, or what we call OH. This guy here, remember, got an additional hydrogen, and that is why it's negatively charged. So the additional hydrogen means the additional electron from the hydrogen that had accepted it. So that is why this guy has that negative charge. It took on negativity. So what happens is we have this base that is called sodium hydroxide. When it breaks apart, it becomes sodium and a hydroxyl ion. So we have a cation and an anion when these guys break up. Sodium hydroxide is a very, very strong base because it dissociates 100% into sodium and the hydroxyl ion. So that's what you have here. Okay, this is your sodium hydroxide. When you combine these two, right, what's going to happen here is that this base, right, or sodium hydroxide, we can combine it with a very, very strong acid. So we have a very strong base and a very strong acid. We can put these two together and we can cause it to react into two very, very safe particular compounds. So now we have salt, sodium chloride, and water. These individually by themselves, you never want to stick your finger in, All right, you actually will burn your finger if that happens. You will cause tissue damage. It's a very caustic chemical, hydrochloric acid and sodium hydroxide. But you put them together, and now what's going to happen is we have this exchange reaction that occurs. The sodium hooks up with the chloride, so now we have sodium chloride, and the OH, the hydroxyl, now hooks up with the hydrogen, and now we end up having water. So this is called a neutralization reaction. So a base is what we call a proton acceptor, or basically it neutralizes this hydrogen ion, right? It chills it out. So bases are able to do what we call buffer, or basically make these hydrogen ions behave that get liberated when they completely dissociate in that water, right? So that's what a base is going to do. A base is a proton acceptor. It'll accept hydrogen ions. When we look at how do we measure this, right? So what is considered strong, what is considered weak? We have this thing that's called pH. The P stands for the word percentage. The H stands for hydrogen ion. So what we are measuring here is the percentage of hydrogen ion concentration in this particular solution. So what's weird about the pH scale, you'll notice that it goes from the number 0 to the number 14. Now, what the chemists did is they used this math that involves this mechanism called using an inverse log, and we're not going to get all into it. But what they did is, instead of using common sense, which is how my brain likes to work, so I told you that this thing says percentage of hydrogen ion concentration. So you would think, hey, if there's more hydrogen ion in something, that means the number, the pH, is going to be a bigger number. However, when you're looking at pH, that is not the case. So, acids, remember, have more hydrogen ion. Bases are going to have very little or none of the hydrogen ion. So what I want you to remember about this, on the pH, the smaller the number, the more hydrogen ion, the more acidic the chemical is going to be, right? So very, very strong acids have a very low pH, but that means that the hydrogen ion concentration is very high. When we go over here to the base, this now means that we have a very low number of hydrogen ion and a much higher number of the hydroxyl. But remember, pH has to do with percentage of hydrogen ion concentration. So, hydrogen ion concentration is high, the pH number is going to be low, so small. If the chemical has a very high pH, that means that the hydrogen ion concentration is very low, right? Low pH, acidic. High pH is going to be basic. And so our scale runs from 0 to 14. Neutral is right in the middle. That's number 7. This is where water sits in. And then you'll see that on this chart, as you go through it, we have blood, which is very important because obviously we have a lot of blood in our body. Blood actually has a little bit of a base component to it. So blood is more basic than it is acidic. It actually sits right here. Its happy place is between 7.35 and 7.45. So again, 0 is the highest concentration of hydrogen ion. So for example, when we measure hydrochloric acid, so 1 mole, which is the unit that we use in chemistry to measure each particular amount of what we have of hydrogen, what we have of chlorides, we put one together. So think of it as like 1 chemical cup, right? Think of it as an easy way of remembering what a mole is. Okay, it's just like a cup, it's like an ounce, it's like a pint, all right? It's just the chemical unit of measurement. So 1 mole of hydrochloric acid, right, would have a very, very high concentration of hydrogen ion, right? So its pH is going to be close to 0 over here. The lowest concentration of hydrogen ion would be like the base, the very, very strong base of sodium hydroxide, right? So that would be over here, close to where 14 is. So the less hydrogen ion that you have, the more basic a substance is over here. The more hydrogen ion you have, the more acidic the substance is going to be, or over to the left. And so that is how they go through and determine how acidic is something or how basic is something else. So things that are going to be more acidic are going to have lower pH numbers. Things that are going to be more basic are going to have higher pH numbers. Easy way to remember this: acidic, if the pH is below 7, it's acidic. If the pH is above 7, it's going to be more basic. But what you're going to be doing in terms of being a paramedic, and what you're going to be learning with how these acids and bases behave in the human body, have to do with what happens in our blood. And so our blood has a very high component of water, and it also has other stuff, right? It has proteins, it has hormones, it has, fats, glucose, and it's also going to have hydrogen ions and OH ions. So we're going to have acidic and basic components within our blood. How much we have within the blood is then what's going to determine, is the blood more acidic or is the blood more basic? So what we're going to be looking at here is, what are the things that cause blood to be more acidic and become more basic? Blood itself at neutral is not 7. Here's 7, right? That's perfectly neutral. Blood, like I said, is going to be over more toward the right, a little bit more basic at 7.35 to 7.45. Earlier, I talked about how we have these things that can accept protons, right? They're called bases. Bases function as buffers in terms of that they take that hydrogen ion and grab onto it and help neutralize it. I always kind of think of a buffer as grandma, all right? Neutralizing the little kid that is going crazy at Target and mom is just losing her mind, right? Things can become very reactive when the kid won't behave. So grandma can go and grab that little kid, that little hydrogen ion, and be like, you know what? Come with me. Let's go do something else. And that'll calm down the little kid, and it also calms down the reactivity of mom. So if you think of a buffer that way, maybe it'll help you understand a little bit of how it is that they can make these hydrogen ions behave a little bit better and not cause so many problems in becoming acidic. The compound that's called bicarbonate in our body is one of the most important buffers that we have. So when we're going to call this acidic or basic, we refer to these terms that are called acidosis or acidotic, and alkalosis or alkalotic. And so acidosis means that with our blood, right, remember pH of our blood, its happy place is 7.35 to 7.45. Remember this, memorize this, know this for the rest of your life, all right? These are really, really important numbers. You have to know that the pH of blood is 7.35 to 7.45. If the pH of blood, right here, gets less than 7.35, now that blood is considered to be in acidosis, no matter what caused it. Right? So if the pH goes below 7.35, we are now in an acidic situation with the blood. If the blood pH goes higher than 7.45, now it's alkalosis. So now it's going to be more basic. And what we need to do in order to bring it back to its happy place is we need to get this pH back down. So we want this right here. This is our sweet spot right here, this blood. You want it to be between 7.35 and 7.45. So you can see that we don't have a whole lot of wiggle room in terms of how much this can vary back and forth. And so what our body will do is it can use carbon dioxide, it can use lactic acid, it can use phosphoric acid, it can use a number of different things to help regulate our pH when it becomes too basic. Or the other way, if our blood becomes too acidic, we can actually use first bicarbonate, which is one of the best bases that we have. We always have extra. It's like we have this account where we deposit all this extra bicarb. It's called our bicarb reserve, and we use that to help neutralize acidity in the body. The body becoming acidic is more common than it is the body becoming alkalinic. And so a lot of the things that we will be talking about in the subsequent chapters, especially when I get to respiratory, digestive, and urinary chapters, is how it is that our body is always trying to maintain this balance between 7.35 and 7.45. Two terms that you're going to need to understand that are very important are when we attach the word respiratory to acidosis or the word metabolic to acidosis. So what happens here is when you have this thing that's called respiratory acidosis, right away what you should think is, oh, this is causing acidity, all right? And so what our blood is going to do is our blood is becoming more acidic, which means the pH is decreasing less than 7.35. And so what happens is that the problem is that we are building up too much carbon dioxide. So when you look at this PaCO2, what this says, it means the percentage of carbon dioxide gas arterially. So how much carbon dioxide is circulating through our blood? Just think of it as carbon dioxide in the blood. We're not going to get picky about if it's the veins, is it in the arteries, whatever. But this is the way that they describe it. Okay, so P just refers to partial pressure of carbon dioxide. So if you get increased levels of carbon dioxide in your blood, this will cause the blood to become more acidic, and it causes the pH to get less than 7.35. So here's our blood. When we get increased levels of carbon dioxide, it causes the blood to go this way, to become more acidic. So when our carbon dioxide level starts to go up, we are now retaining carbon dioxide. It makes the pH go down. So here's another number that is really important for you to remember. Normal carbon dioxide level in our blood is between 35 to 45 millimeters of mercury. You've probably seen this when you're looking at end tidal output on a monitor, right? There'll be an EtCO2. You'll look at this number and you're like, oh, it's between 35 to 45. That is our happy place. If the number is increasing greater than 45, that means that that person is retaining more carbon dioxide than they should. And what that's going to do is that it's going to cause the acidity in the blood to increase. So what happens when you have respiratory acidosis, the thing to blame that is causing the problem is you are retaining, holding in too much carbon dioxide. You're not exhaling out and getting rid of the carbon dioxide in the proportion that you should be. So if you think about this, that will mean that a person is not breathing properly. They are not inhaling properly to bring in that oxygen, and they are not exhaling properly to get rid of that carbon dioxide. So the carbon dioxide builds up. When you put the pulse ox on the person's finger and you're measuring, right, you're doing an estimate of, okay, what is the concentration of the hemoglobin with oxygen? Well, yeah, it could say 98%, it could say 94%, it could say 97%. But here's the thing with that little unit, that little thing is not only measuring oxygen. It measures the concentration of hemoglobin. Hemoglobin is a protein on a red blood cell that can carry more than just oxygen. You can have carbon dioxide attached to it. You can have carbon monoxide attached to it. So all you know from the little pulse ox is that hemoglobin is either concentrated or it's not. We make the assumption that it's oxygen, but that isn't always the case. All right? So what you need to remember when you're looking at what is respiratory acidosis, we are going to be looking at the end tidal carbon dioxide. What is the CO2 doing? And the number that you need to remember is that normal end tidal is between 35 to 45. It's giving you an estimate of what it is in terms of the carbon dioxide concentration in the blood. So if you retain carbon dioxide, that means that your breathing is affected. The respiratory rate is, it could be low, right? You're not breathing as often, or you're breathing shallow, which means you're not taking in enough air and being able to get rid of enough air, or you're breathing very, 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 very little, right? You're not breathing frequently enough. So anytime on a scenario question, on a test or a quiz, you're looking at it and it says labored breathing, shortness of breath, or apnea, or bradypnea, all right? Those are words that are going to tell you that the breathing, the respiratory rate is affected. And that's always going to mean that you have retention of carbon dioxide. You're not getting rid of it. When we have metabolic acidosis, now the problem that is causing the blood to become acidic is not carbon dioxide. I'm going to say that again. With metabolic acidosis, the problem is not retention of carbon dioxide. Something else is causing the blood to be acidic. So it could be excess production of lactic acid. It could be that this person is in diabetic ketoacidosis, which means that they are now using fats, which have a fatty acid attached to it, that is causing the blood to become more acidic. That is a real common thing that can happen with people who have type 1 diabetes. So what happens there is that the blood is becoming acidic, right? The pH is dropping. It's getting less than 7.35. But the problem is something else other than carbon dioxide is causing the issue. Now, in the field, you are not going to be measuring bicarbonate level. It is not what we do. So the only thing that we have to measure what happens in a person's exhale, right? When they exhale out, we have carbon dioxide levels. So the amount of carbon dioxide can tell us, is this person acidic or not, right? But when somebody is in metabolic acidosis, you don't know what exactly caused the acidosis. We know it wasn't carbon dioxide, but it's something else. But the cool thing is that our end tidal will tell us, hey, this person is acidic, right? Because the end tidal will say, hey, we have this person trying to get rid of acid. And it comes out in the form of carbon dioxide. And I will explain how that works in a little bit. But the thing to remember here is metabolic acidosis is the pH is dropping, so they're becoming more acidic, but the problem is not carbon dioxide. It's something other than carbon dioxide that is causing the problem. I give you these numbers of what bicarb levels will be measured as in the hospital, just so that you understand that this is one of the ways that they're able to determine, is this person in metabolic acidosis. They will draw blood, and one of the things that they measure is bicarbonate concentration. When the bicarb is low, remember this is a base, that means that the hydrogen ion is going to be high. Okay, but in the field, again, we are not measuring bicarb levels. All right, all we have is our end tidal. But because our body tries to get rid of acid by increasing our respiratory rate, which means we can increase how much carbon dioxide we exhale, we can have an idea if this person is in acidosis or not. So, to summarize, respiratory acidosis, carbon dioxide is the problem, right? So if the carbon dioxide levels are high, which means they're abnormal, greater than 45, that means respiratory acidosis because the pH is going to be less than 7.35. So when you're measuring your end tidal, in this case, you would have a greater than 45 number on the monitor, and that will tell you, hey, this person is acidic. If the problem is a respiratory problem, shortness of breath, labored breathing, not breathing, right? They're retaining carbon dioxide. It is staying inside them, right? That will cause respiratory acidosis. We had too much carbon dioxide inside. Metabolic acidosis is something other than carbon dioxide causing the problem. The issue is low bicarb. We don't measure bicarb levels in the field. So the things that can cause metabolic acidosis are acids that we produce in our body. That would be lactic acid, right? Example of that is obviously when you do anaerobic workouts, high intensity workouts, you feel that burn in your muscle. That is that lactic acid production, all right? That can cause metabolic acidosis. Or our bodies are using fatty acids primarily for energy. In the case of type 1 diabetics that are insulin dependent, the body will shift into fatty acid metabolism. It'll make ketones. Part of that molecular process that occurs with the different reactions is that it uses the fatty acid component of the molecule to make carbon, and take that carbon and then put it into the biochemical pathway to be able to make energy, or ATP, that our cells need in order to survive. And so the body goes into this metabolic acidosis. Alcoholics, when our body is going through and trying to process the ethanol from the alcohol that we drank, our liver will produce acetic acid. So alcoholics can be in metabolic acidosis if their liver is not able to keep up proportionately with the amount of alcohol that is having to be dealt with. So again, remember, respiratory acidosis is a respiratory issue. The problem is this person is not breathing properly, in that they're breathing, the rate is either too slow, it's too shallow, it's irregular, they are retaining CO2. CO2 is the problem. Metabolic acidosis, CO2 is not the problem. Some other acid in the body, lactic acid, fatty acids, acetic acids, it could be phosphoric acids, it could be breakdown of amino acids from protein. Something else is causing that hydrogen ion in the blood to be the problem. So that's the big difference between these two. When we go to the opposite side of the pH scale, we now get into the basic. Now we can have respiratory alkalosis. Again, respiratory rate, something is going on with the person's breathing. But now what happens when you get into respiratory alkalosis is that your body does not have enough carbon dioxide. So what happens here is that the carbon dioxide level gets too low. So when you hyperventilate, and that is always going to be your big key word, and when you're reading these scenario questions, hyperventilation, rapid respiratory rate, all right? When that is happening, when they're hyperventilating, right, respiratory rate, above 20, when you get into the 30s, the 40s, right, with an adult, they're blowing off too much CO2. So the CO2 level is getting too low in the blood. That causes the blood to become more basic. So what will occur is you'll look on your end tidal and it'll show that the end tidal number is less than 35, which means low CO2. When you have low CO2 in the blood, that means pH, the pH level in our blood is going to be moving to the right. So it's going to be greater than 7.45. So a low CO2, high pH, that means we are in alkalosis. If the problem is a respiratory issue, which means they hyperventilated, that is your key word, then it's respiratory alkalosis because the problem was a respiratory issue. And the end tidal will tell you that the end tidal carbon dioxide is low, under 35. If we were to measure the pH, it would be greater than 7.45. When we have metabolic alkalosis, now the problem is not carbon dioxide. Now we have too much base in the blood for some other reason. So things that can cause this. For example, taking too many antacids, right? You eat something, your stomach burns, you get heartburn, you're popping Tums and Alka-Seltzer and things to help neutralize the acidity in your stomach. Those things that you're taking in are called bases. They neutralize the acid. So when that happens, taking too much of that can actually cause the blood to become more basic, and it can cause metabolic alkalosis. The other thing that can be caused by this is vomiting too much. So when you think of vomit, right? Vomit comes from the stomach, right? We have acid in our stomach. So if we vomit too much, we can become too basic in our blood. So that can also cause metabolic alkalosis. So the problem here again is not carbon dioxide. The problem is that something is causing our bicarbonate levels to be too high in the blood. And again, in the field, you are not going to be measuring what is the pH, right? All you're going to know is, hey, this person's either exhaling enough carbon dioxide or not enough carbon dioxide. When we get to how this works, right, in terms of the respiratory rate and the respiratory equation, it'll make a little bit more sense. But for our purposes for right now, what I want you to remember is respiratory alkalosis. The thing we blame is a respiratory problem. The issue is we don't have enough carbon dioxide. So you exhaled too much carbon dioxide. So if you were to measure end-tidal, you would have a low end-tidal volume, or value, less than 35. pH is going to be elevated. If it's a metabolic alkalosis, something other than carbon dioxide is causing the problem. So our problem is we have too much base in our blood, right? And so what is happening is the pH is going to be high. So it's going to be greater than 7.45. And we would also, if we were to take blood work, and we do that at the hospital, then the bicarb level will come up high, all right? So that's our respiratory and metabolic alkalosis. Now, when we move into just what do these molecules look like? Now, I'm not going to test you on, when you look at a molecule, is this a sugar? Is it an acid? No, that's not our purposes. But I want you to understand where this comes from, because this biochemistry that takes place in our bodies and how we utilize energy and how our body can become acidic and how it can become alkalinic has to do with when we break apart these molecules. So a carbohydrate, ultimately what we want is we need carbs for energy for ourselves. It's the number one source of energy that we need in order to be able to make energy. So when our body takes a sugar, okay, so this is an example of what a glucose molecule looks like. And when you look at a molecule, an organic structure like this, when you just see these little lines that have nothing attached to them, all right, what is attached here would normally be a hydrogen ion. Each one of these little corners on this little hexagon is a carbon, all right? So this is your structure for glucose. You'll notice that when we take glucose and we bind it to fructose, which is another type of sugar, we actually have these two molecules that are kind of hanging out together. So we can take these two and we can do a dehydration synthesis reaction, which just means we dehydrated these two. So we take this molecule, right? We have these two guys together, we put them together, and we take an OH from one and an H and make water. And now we take one of these O's, this little guy right here, and we use that O to make sucrose. So when you combine glucose plus fructose in a dehydration synthesis building, we make the molecule called sucrose. This is the sugar that you add to your coffee, right? The byproduct of this reaction ends up being water, right? But it's called dehydration synthesis because we removed water here and made our molecule, all right? Now if we go the other way, so now we're going to put them back into their individual units of fructose and glucose. Now we add water to sucrose, and we end up with using a hydrolysis reaction, which means we broke water. This word lysis means to break. The word hydro means water. And again, this is where I'm going to be pointing things out to help you guys understand some of the medical terminology you're going to be coming across. For example, here mono means one, poly means many. So we took water, hydro, we added it to sucrose, we caused a hydrolysis reaction, hydro removal, and we now have glucose and fructose. So we took water, boom, removed water, and now we made our two little compounds. So in hydrolysis, just remember we are breaking down little molecules by adding water molecule, and in a dehydration we got it removed. So our carbs, just remember this, mono means you have one sugar, di means you have two, poly means you have many, right? This is an example of starch, right? So potato, for example, is a polysaccharide. So it has a lot of these sugar molecules all bonded up together, so very long branching chains of simple sugars. So this would be an example of a complex carbohydrate. Proteins look very different, right? So what you have in a protein, what is unique about a protein, is this little piece right here of the molecule. This is called an amine. So when you have NHH, it's called an NH2. So this is an amine group. This is what makes this an amino acid. On the right, this COOH, this piece is what makes this little compound an acid. So when you have an amine, over here, NH2, and COOH bonded to a carbon, now we have an amino acid. So this guy right here, this is its own little unique guy, and this little R up here just means it would have other carbon thing attached to it that would give it, its unique structure, all right? So proteins are little compounds, and our amino acids, there's 20 of them that our body needs to make stuff, has an amine group, the NH, and an acid group, the COOH. This hydrogen ion right here is the thing that we blame for when we use protein for energy that can cause acidosis. So this is why when you're breaking down protein, your blood can actually also become acidic. When you look at how proteins are shaped in the body, and again, I'm not going to test you the different shapes of the protein. For our purposes, it doesn't matter. You will never run on a emergency where the protein shape changed. Oh my God, right? It's never going to be the case. But primary protein just means you've got these little units that are just linked together like a little, pearl necklace, right? A secondary protein just means that now the protein itself has actually bent. So instead of looking like a nice little chain like this, now we have these like little sheets in terms of where they got bent. And now we've brought in other components that cause this kind of folding to take place. A tertiary protein, this right here is an example of, for example, a transport protein, like something that would transport thyroid hormone, right? Tertiary proteins are going to have more of a global or a little globe type shape with foldings within. And then what we have, what's called a quaternary protein. Quat means 4, ter means 3. So in this case, this type of protein, this is going to be the most complicated shape that we can have. This is what hemoglobin looks like. So this is an example of what hemoglobin would look like. So it's got this component of 4 different chains. So we're combining more polypeptide chains into the mix. So that's what you would see here with quaternary. So it's just the actual shape of the protein that changes. We can still break this up into the individual amino acids that built this and use the carbon that's in the amino acid for energy. But remember, whenever you burn or you use amino acid for energy, you're actually increasing acidity in the blood. Then in terms of the type of proteins that we have, and when we get to the immune system, when we get to the endocrine system, we'll be talking a lot more about this. They fold into the particular structures that our body uses. For example, with our immune system, antibodies are very important functional proteins. Transport proteins are very important in terms of transporting things that are repelled by water. So like in our blood is mostly water. So there are certain compounds that cannot be transported in the blood just freely dissolved in it because it just wouldn't work, right? So you need to think of it as a little inner tube to help it be in its happy floaty so it can get transported to the tissue that it needs. And then enzymes, remember, enzymes are catalysts, which means they make reactions happen more easily by decreasing the amount of energy that you need to activate that reaction. So these are considered to be functional proteins. An enzyme looks like this. So here's your enzyme, right? So think of it as a facilitator. Here are the things that we're going to cause to react together. So we call them a substrate in this particular case, or you can think of it as your reactants. So we put them together with this enzyme, and now what's going to happen is the enzyme actually causes this reaction to happen more easily, and it forms our bond much more easily. So we took these, say, 2 simple sugars. Remember when we did this dehydration synthesis? We used an enzyme to make it happen faster. Like, for example, when we make our molecule to make sucrose, okay, we took glucose plus fructose, so this could be glucose plus fructose. We're going to remove the water when we get this enzyme to react, so we use sucrase to do this, and then our body goes through and causes the reaction to happen, and now we have our little disaccharide, or 2 sugar molecule, and we removed water from it. So again, enzymes, the main thing that I want you to remember from this is that they lower the activation energy needed for the reaction. Then lipids, these are fats. They're going to contain carbon, hydrogen, and oxygen. What's going to happen here is that in some cases they're going to have a COOH attached to it, which is going to make part of that molecule be a fatty acid. And so we can use the carbon portion of the molecule for energy, and I'll show you that in a second. Things that are lipid-based substances, for example, vitamin A, vitamin D, vitamin E, vitamin K, these are fat-soluble vitamins, which means they can be dissolved and stored in fat very easily. These things that are called prostaglandins cause smooth muscle contractions. These are very important in terms of things that take place in the uterus, along our GI tract, with regulating our blood pressure, immune response, pain receptors. So very important chemicals. Lipoproteins, you've heard of these. Most everybody thinks of these as, oh, my cholesterol, right? So you've got the good cholesterol, which is called high-density lipoprotein. Bad cholesterol would be our LDL, VLDL, which just stands for low-density lipoprotein, very low-density lipoprotein. This just means that they have more fat, more lipid than they do protein. So the H here in HDL means high-density lipoprotein. So these aren't going to get stuck as easily in our blood vessels as these LDL and VLDL do. If you want to learn more about that, that's another course, nutrition, that you can take. Something that's called a glycolipid. A glycolipid is a molecule that is going to have glyc, which means it's going to have some kind of glucose component to it with a fat attached to it. And these are kind of like name tags that live on the cell membranes. We can also have glycoproteins, for example, that are proteins that have glucose components with it. So it's just little markers that are like little name tags on our cells. So this is just an example of what a triglyceride looks like. So this is glycerol. So you're going to have these carbons right here. These are important in terms of how we're going to use them for energy. And then this little piece over here, the CO, and then OH would be right here. This component that you're seeing, this is the piece that becomes the fatty acid. So all of this right here, right, this portion is what our body, when you start using fat for energy, for example, with type 1 diabetics, they can't use glucose, they can't absorb it into the cell. When the body is not able to take that, their insulin level, for example, is not high enough to bring in the sugar, and they end up having way too much sugar on the outside, then the body will resort to the fatty acid metabolism pathway and start using this carbon skeleton to then be able to make ATP. But what it's doing is that it's actually breaking off this piece of the molecule, and then part of this is going to be acidic, and then that's what ends up causing the issue. When you think of a saturated fat, this is going to be solid at room temperatures, like animal fat, butter, the yummy stuff in a ribeye. When you look at the solids at room temperature, so like I said, butter, lard, bacon, all that stuff is considered saturated fat. This is going to have more cholesterol. This is what causes more of that low-density lipoprotein. Unsaturated fats, these are going to be liquids at room temperature, so like vegetable oils are going to be this. So what's happening is that when you look at what does the chain look like, okay, this one is all little single bonds, so these are called saturated, right? They're saturated with hydrogen ions, so hydrogen bonded on each of these little ends has hydrogens on it. This little guy here is unsaturated, so it's going to have a double bond here, which means it doesn't have as much hydrogen. So that's really all it is. The structure of the chemical, structure of the molecule is what makes it liquid because of these little double bonds here. Everything else that you see on this part, right there on the molecule, is very similar to what you see with the actual saturated. So it's just how the thing is shaped. So I talked about what these little markers would look like on a protein. So this is on a cell membrane, sorry. This is an example of what a glycoprotein would look like, or a glycolipid, All right, these would be sticking out. These little yellow guys in here, these are embedded inside a cell membrane. That's cholesterol. All right. And then a phospholipid, the word phospho in this word phospholipid means phosphate. So when you look at a cell membrane, all right, phospholipids are what make up our cell membranes. What we have is this outer component of the actual cell, all right, the outer portion of this part of the membrane. This has phosphate. And then this piece that is sticking down, all right, these are the little legs. That's these little things. These guys kind of look like jellyfish, right? This little circle, right, each one of these little units, that's a phosphate. And each one of these little things that look like legs, that's the lipid portion. So that's what we call the phospholipid. So what happens is this outer portion of our cell membranes, all our cells, they like water, right? They're cool with water because phosphate actually is a negatively charged particle. When you have your lipid portion, lipid, you can't take oil and water and mix it together. So this inner portion of your cell membrane doesn't like water. So when something likes water, so like out here, right, the phosphate side of the molecule, it's called hydrophilic, water-loving. Hydrowater-philic love, all right? It interacts with water just fine. When we have the phobic portion, it does not like water, so this piece, the inner portion of our cell membranes, these are all fat. So these can't have water-containing compounds that are going to pass through very easily. So when you see these little things, these purple things depicted on here, these are gates. What they are is that they are protein channels. And so we have these little passageways where we can actually have these doors that open and close and allow things to pass through that would normally not be able to pass through the fat-containing area. So they're just considered these little gates that allow things to come in or keep things out. And so our cell membranes are made up of a biphospholipid layer, which means here is a phospholipid, phosphate and lipid, and the inside of the cell, phosphate lipid. This portion on the inside of the cell has a lot of water. So that is why we have the phosphate side of it on this side. Then steroids. Steroids are compounds that are made up, the base ingredient is cholesterol, so that is what you're seeing right here. This is a steroid, so it has ring-based structural molecule, organic molecule, and this is the basis of the ingredient for the hormones that are called steroid hormones. For example, aldosterone, testosterone, progesterone, estrogen. All those hormones are steroid-based hormones, and their base shape comes from cholesterol. So when you're taking a cholesterol-lowering medication, it can actually impact the production of testosterone, of progesterone, of estrogen, of the more steroid-containing hormones that are very important for our body. So that's why you want to be careful when you're actually taking some of these medications, because it can then affect the steroid hormones in the body. Then these things that are called nucleic acids, they are built from these units that are called nucleotides. And the best example I can give you for this is the DNA that's in our cells. Our DNA is our genetic blueprint that is going to dictate how is it that our body is going to make proteins. And so what a nucleotide is that it contains three parts. We have this thing that's called a nitrogenous base, all right? So like, for example, this guy here, cytosine, guanine, these are all going to be your little nitrogenous bases, okay? And then we're going to have a sugar. So it's either got a sugar with oxygen or without. So when it says deoxyribose, deoxy means without oxygen, and then a phosphate group. So when you have this, what we're looking at is the base that you would see with DNA, okay? So it's deoxyribose nucleic acid, and they all have these base components, but the actual nucleotide of the base itself, all right, is going to be different. So like we have this thing called cytosine, guanine, adenine, uracil. This is going to be on RNA. And then on this side, on our DNA, we have cytosine, guanine, adenine, and thymine. And so you'll notice that over here with our RNA, and we'll get to how our body uses DNA and RNA and how it's able to duplicate and do the different things, has to do with how do these guys pair up. So our DNA, if if you look at it here, you see how these little colors of what they're depicting the bases to be, they have their specific pairs. Guanine and cytosine like to pair up. Adenine and thymine like to pair up. But you're not going to have adenine pairing up with guanine. It's just not going to happen. They don't hook up. They don't get together. And so it's kind of cool how it is that our body's able to make the copies from the DNA here using the copy machine, which I like to think of. RNA is kind of like when you're going to push the button and make your copy. It's these little bases that are sticking out of their little RNA that will then go and copy one strand of what's over here on the DNA. And then it tells the cell, hey, you need to make more of this particular protein. So it's really cool how it's able to do that. But these nucleic acids have an acid component to it. And that is why when our cells break up, we are also adding a little bit of acid from this. Not significant amounts like we do when we break up fatty acids and amino acids, but we still have a little bit of an acidic base to this. So DNA, like I mentioned, it's a double helix, so it means that it has two little strands of ribbon. Attached to the little ribbon are the little bases that are going to pair up and only pair up with the base that they like. All right, and so here we have adenine and thymine, cytosine and guanine, they pair up, and we'll get to that when we go through how it does its thing. And then I said RNA is what allows for the copying of the DNA structure to take place. And so how it does this, it's a process that's called transcription and translation. So basically what happens is the RNA molecule will go into the nucleus of a cell and copy the DNA sequence that it needs, that it's been directed to do. And so what it does, and why it's called transcription, is that it's transcribing, that's called copying, that portion of the DNA that it needs, and then it leaves the cell, so it's called messenger RNA, mRNA leaves, and then it goes to this protein structure that's called a ribosome, so that's what you see here, and it'll translate, right, what the code was that it copied. And so what it ends up translating is that you have the little codes based on what is the protein that we need to make. And so protein is coded based on three little bases. So like for example, this one, CUA, is the code for an amino acid called aspartate. Okay, over here, phenylalanine is the code that has AAG. And so what happens is, as this little guy is passing through this ribosome, it's saying, hey, now I need AAG, right? And so now AAG is going to be brought in to the sequence, and then you're going to be making the protein. And so what the body does is it copies based on the message. So here's your DNA template that you copied. Here is the messenger RNA. This is the message. And then each one of these three little units of the code mean a particular amino acid. So like this one, TRP, tryptosine, phenylalanine, glycine. I can't tell which, if that's a G or an S. But so that is what you're coding on here. And so you make your code, and then the transfer RNA is what brings the amino acid in to then start building the little protein. And you can go on YouTube and watch, transcription and translation of, cell replication. It's super cool and fun to watch. You become a biology geek like me. Then ATP, I talked a lot about this already. ATP is what our body needs for energy. So remember that it's going to have a base. So here's our adenine base. It's going to have the sugar, ribose is the name of the sugar, and then phosphate groups. And ATP means adenosine triphosphate. So it means it has three phosphates that are attached to it. So the three phosphates, what they're going to do is, in order to use ATP for energy, we are going to bust open or break one of the bonds between these phosphates. And so how this happens is we do this hydrolysis reaction. So what we're doing is we are adding water. So we're going to add water and break it up. So we're going to lyse the water. And in doing that, we are now going to break off a phosphate, and we're going to make this unit, remove the phosphate that's called ADP, adenosine diphosphate, because we just took one phosphate off. And when you break that bond, boom, you get energy. Use the heat from the breaking of the bond that allows for the cell to continue its different reactions that it needs. So ATP is cellular energy, and we'll get into how it is that it works and how it is that our body uses it and what type of biochemical process it needs to use in order to make the most ATP. And so this is where it's important that you understand why do we need oxygen and what happens when we don't have enough oxygen and the type of metabolism that our body's going to go through. And we'll talk about that later. So ATP facilitates work, right? So we're going to break it up and it helps us make different compounds, right? So we're going to be able to break things up, build things up by using ATP. ATP is also used to run the gates that actually manage what comes in and out of certain cells. So when we need energy to be used for this, it usually means that something that is coming in or out is going against the current, so we need to use ATP for that. And in some cases, we need to use ATP to do mechanical work. So like when you need to contract a particular muscle, you're going to be using ATP for that. So ATP is absolutely essential for our body to be able to make it. We cannot make enough ATP in our body without oxygen. So this is why when we don't have enough oxygen, our body's metabolic rate is going to suffer, because what you're actually doing is you're impacting the ability for the metabolic pathways in the heart, in the brain, in our organs to function, to continue doing their job. When the body can no longer make ATP, you're going to die, because the first thing that's going to die is going to be the brain. That is going to be your biggest user of glucose, your biggest user of oxygen. Then comes your heart, and then it starts affecting the other organs. We cannot survive without oxygen, because we need oxygen to make the massive amounts of ATP that our body needs in the tissue, in the cells, in order to be able to continue to generate the energy that it needs. So that's the end of the chemistry chapter. If you have questions, again, please get in touch with me. I think that the lab that you will be doing will be helpful for this. And the next set that we're going to be talking about is going to be the cells and the tissues. And a lot of what you saw here is now going to come into play in terms of how it is that cells function and how the tissues are able to go through and conduct metabolism.